Welcome to the Engineering and Construction webinar series. My name is Mucklow, your host. With me today we have Tapan Patel. Today's webinar will discuss the use of Modified Atmosphere Insulation, MAI, which is a type of vacuum insulated panel. The MAI has been installed in a facility at Fort Drum in New York, and the goal is to demonstrate the procedure for installing MAI and validate its performance through modeling and validation. This webinar will focus on a case study that will include the following topics: the installation process, the performance data on the MAI panels, EnergyPlus modeling of the MAI panels, and validation of the energy models using sensor data. Our presenter, Mr. Tapan Patel, is a mechanical engineer with USACE, Engineer Research and Development Center, and the Construction Engineering Research Laboratory in Champaign, Illinois. He is involved in facilities research, including building envelopes, HVAC systems, and energy modeling, and is leading several projects that aim to develop and validate the cost effectiveness of emerging envelope and HVAC technologies. With that, I will now turn it over to Tapan Patel.
All right, well, good afternoon, everyone. My name is Tapan Patel. As Eric mentioned, I'm from the Army Corps CERL. We're located in Champaign, Illinois. I'm a mechanical engineer within the energy branch, and I'll be presenting today on modified atmosphere insulation. But before we get into that, real quick, our agenda here, the overall goal of this webinar here is to really discuss the implementation and the modeling aspects of MAI. So keeping that in mind, there's a few objectives we have as part of the program that funded this work. I'll talk a little bit about the installation process, what we need to consider or think about when we're installing these panels, and then I'll go into some details on the modeling and validation process. The goal here, again, is to hopefully give everyone an overview of a start to finish of this technology and some of the considerations that we need to be thinking about when it comes to implementing this technology. I'd like to acknowledge several folks here from CERL helped me on this project and this technology, as well. Oak Ridge National Lab, they're leading the design and analysis of the technology, as well as some of the energy modeling efforts. Fort Drum is our case study site here. Mr. Steve Rowley is the energy manager there. He supported this effort and has helped us tremendously with the coordination. Nano4 Inc. is the supplier, the technology provider, and ESCPP here is the funding agency that allowed this project to be conducted. So a quick background on MAI. MAI, again, stands for Modified Atmosphere Insulation. For those of you that are familiar with VIPs, Vacuum Insulated Panel, this is a new technology, or relatively new technology, that's really represented a stepwise function in insulation. VIPs generally have a rigid structure, and you pull a vacuum around them, and so when you have a vacuum, you're really severely reducing your heat transfer, and that's what gives this material such great insulated properties. So in Figure 1 here on the bottom left, you can see that compared to a lot of our traditional insulation technologies, you can typically achieve at least R36 per inch. Compare that to polyiso, which is probably the next closest technology, and that's only R5 to 6 per inch. So really, again, this is a stepwise improvement in insulation. One of the challenges with VIPs is they are relatively new, and so the cost of VIPs is still pretty high. In most cases, it does not make sense economically to install them. So what we're looking at here is MAI. It's a simplified manufacturing process, and I won't go into too many details, but really the manufacturer here in this case has 50% fewer steps to make these panels. And so what that means is you can decrease the cost of these panels by up to half compared to traditional VIPs. So in order for us to think about implementing these panels, obviously it has to make some kind of economic sense, and this is kind of a step in the right direction. I will mention here that, and even though this technology is, MAI is projected to be cheaper than traditional VIPs, it is still a little more expensive than polyiso on a per square foot per R value basis. So there is still some room for improvement, but again, this is a step in the right direction. Here are some characteristics that we've measured of these MAIs, and one thing I'll mention here is I'll use VIPs and MAI interchangeably throughout the rest of this presentation. Although we did test MAIs for this project and this work, I think most of the lessons learned here and the modeling efforts are directly translatable to VIPs. So I'll go ahead and use those interchangeably. But generally, because it is a vacuum product here in Figure 3, you can see that the R value will decrease as a function of temperature. So temperature here is on your x-axis and R values on the y-axis. And the reason for that is as you're increasing your temperature, the partial pressure inside your panel, it's not a perfect vacuum, so there are still some molecules there. Your partial pressure increases, which increases the conductance, and therefore you have decreased R value. But nevertheless, even at in very warm climates, you can still achieve roughly R34 per inch. So that's still very good. The other factor that we need to consider here, and this will come up later, is because it is a vacuum panel, it's very easy to puncture these things and really destroy their effectiveness pretty easily. So this is a graph that shows the R values here on the y-axis and pressure inside the panel, and you can see that as the pressure increases, as you'd expect, the R value also decreases. The important thing to note here, though, even though your pressure may increase and come close to atmosphere, the overall R value is still slightly higher than conventional insulated materials. But as we discussed earlier, the cost, again, it wouldn't make economic sense to implement something if these panels have failed. So the learning objectives for this webinar, as I discussed a little bit earlier, the first thing I'd like to point out is we'd like to describe the expected impacts. Again, the VIPs are very good. They have a very high R value, but we want to understand what this means in terms of energy consumption. That was goal number one for this effort. Number two is also to model and validate our expected savings against what we see. So we'll talk a little bit later. What we did is we installed a lot of sensors in the facility, and we're in the process of validating our energy savings against the models. And the goal here is, once we understand how to model this technology, we can transition those lessons and the things we've learned to other folks who are interested in modeling and validating the technology. So our case study here for this demonstration effort was Fort Drum. The reason we picked it, it's a primarily heating-driven climate, which means we really expect to see a lot of the value come out of these panels. Number two, prior to this effort, we had not really considered, and even in this effort, we have not considered the impact of moisture migration. These panels are covered with almost like it's a non-permeable membrane, and so what that means is in warm climates with the humidity, we could have some unwanted effects with moisture migration. And so up in Fort Drum, it's pretty dry, it's pretty cold, and so that was one thing we knew we needed to avoid. The demonstration here, we had two facilities. Figure 5 here, they're very close to each other, very simple buildings, 2x6 construction, R13 in the walls, and R40 in the roof. And the reason we chose these buildings is they're very simple, as you can see in the picture here in Figure 6. This pretty simple rectangular building. There's not a whole lot of windows or doors, and so what this means is we can easily model the building, but more importantly, it's a small building, and we can control our variables relatively well compared to a larger facility. It's also a classroom space, so what that also means is we have pretty good knowledge of the occupancy. These classes are regularly scheduled. If they're not scheduled, we know we don't expect anyone to be in the building, and so that really helps us constrain and control some of our variables when it comes to the modeling aspect. For the CSTCP project, our performance objectives primarily were to demonstrate and validate the energy performance. The goal here is to transition this technology if it's successful and to spread our knowledge and the lessons learned from this project. So what we did is we took one facility, and I'll go back to my previous slide, facility 432B, that's the retrofit facility. We put the MAI panels onto that building, and 431B was our baseline. And so we had two buildings very close to each other, operate almost very similarly, one with the panels and one without the panels. We put sensors, electric, gas, temperature, relative humidity, and heat flux sensors in both facilities. And our goal is to compare the data we receive with the sensors and compare that to our EnergyPlus models. The reason we chose EnergyPlus here is, as you may know, it can get very complex, and there are some considerations that we really need to account for. So it really helps us to understand how the facilities are performing, because EnergyPlus can get pretty complex. There are things that we hope to transition, and so other folks can use more simpler modeling software that they choose to do that. And we'll get into that a little bit later. Our technical objectives here were to demonstrate the overall reduction in energy consumption and quantify that reduction, as well as also the electrical demand and the energy loss. The energy loss through the walls was measured through heat flux sensors. Our other goal as well is to improve the R value of the wall by roughly R14 per inch. So the existing facility already had, if you account for thermal bridging, already has roughly R14 per inch, and so we're essentially doubling the insulation factor on these facilities. So taking a step back, our first goal and challenge to some extent was coming up with a plan to install these. Compared to traditional polyiso or fiberglass, it doesn't make sense to put this in the cavity because the only purpose that will serve is further enhancing your thermal bridging. We really wanted to cover the exterior of the envelope and reduce that amount of thermal bridging. The challenge here is, in these facilities we had a metal sheathing, metal panels on the exterior. You can't see it in this picture because it was taken off, but when you put them back on, the fasteners that are used, the screws, we want to make sure that we don't penetrate these panels because they'll lose their vacuum. And so in the top left here in figure 7, what we started with is we went out and got measurements from the field of these facilities. The red dotted lines, not sure if that's coming through on this slide here, but the red dotted lines are the locations of the fasteners. So we wanted to make sure we avoid those, because when the metal panels go back on, we're putting screws through there and we don't want to damage our panel. So really it was almost like a jigsaw puzzle or a Tetris type endeavor to try and put all these panels and make sure we stick to our plans when it comes on site. So as you can see in these comparisons here, we did pretty well. The procedure here was to use some Gorilla Glue on the back of these panels, stick them on there, and by the time we got around, they held pretty well on the wall. We actually cut the polyiso on site. It made things a lot easier because there were some things that we didn't account for, some distances that were different than what we measured. So we just had a table saw on site and we cut it on site. You may notice here these black strips right here are zip tape. The reason we did that is to A, holds all the panels together, but B, we wanted to get rid of any small air currents or anything of that nature that would kind of reduce the overall effectiveness of the panels. We haven't had a good way of testing that, so we don't know how effective that has been. We wanted to do it as a preventative measure. It's not clear at this point if it's absolutely necessary, but again, this was a demonstration and we're trying to get some good data, so we decided to go ahead and be a little more careful while putting these on. So one question that came up during our demonstration here is, once we put these metal panels back on, how do you know if a panel is failed? When you're out there doing the work, putting the panels on, it's pretty easy to puncture them if you're not careful. In fact, during the installation process, we punctured about 3 or 4 inadvertently. Somebody stepped on something, somebody dropped a pen, and it punctured the panel, so we have to be really careful. But after we put it back on, we had to know, and we wanted to know, how well we did, and secondly, also whether any panels had failed. So it turns out, and this is good, it turns out that IR imaging actually works pretty well for this case. I'll start here on the top right figure. There's 2 spots on the slide here, spot 1 and spot 2. If you read the temperatures, spot 1 is about 35 Fahrenheit and spot 2 is about 36. And so you can also see a kind of a color difference in those 2 areas. The purple area, spot 1, is where we have the MAI panel, and we can see that it's cooler. Keep in mind this was in the winter, and so there wasn't as much heat in that spot escaping the building. Here in the bottom left, we see the same thing. Spot 1 this time has a failed panel. The rest of the facility here is a little bit darker shade of orange. That's we also had panels there. Those panels had not failed, and so you can pretty well see a clear contrast here of the failed panel versus the panel that's intact. And if you read the temperatures, you can also identify it that way. Incidentally, you can also see where we had put in our polyiso here. These are some of the yellow strips right here. These are where the fasteners went, and you can see that pretty clearly. So that's one of the important lessons we learned here. We weren't sure how effective this would be, but it turns out it actually works pretty well. So IR imaging is a good method, at least in this kind of facility, to validate and make sure that your panels are still intact. Ultimately, what that does is, for example, if I had lots of failed panels, that would affect my energy modeling. So that was during the installation phase, and we have gone back periodically to conduct IR imaging. One of the reasons for doing that is we want to know, how does this stuff hold up over time? One of our concerns is that there could be a slow puncture or slow leakage into the panels, and we may not notice it right away, but after a month or maybe 2 months or so, as the air starts entering the panel, eventually it'll lose its effectiveness. One other item we didn't account for, and this is another lesson learned, is coordinating with the facilities and the owners of the facilities. Before we had completed our work, we'd sealed everything up. After we left site, some DPW staff had come in and put these new signs on. And so, as you can see, just looking at the building, you can't tell that there's anything different. But we did have panels in those sections, and so this darker square here is where the sign went up. And so the panels that were behind it, this top row here, and the panels behind this sign, they were all damaged because they were screwed into. So that's an important consideration there. Again, it wasn't a terrible loss on this facility, at least. We had a total of 6 panels that were damaged from these signs. there were an additional 6 panels that we found later on that we may have inadvertently damaged during the installation. And so that 8 months after our installation, we've got about 12 total panels that have failed. And that's out of 330, so it's not a bad percentage. We're looking at about 3 or 4 percentage points that have failed, which is about what we're expecting and really hoping for less than that. So the other aspect I'd like to mention is, of these 6 panels, we only noticed 1 of them right after the install. So when we came back a few months later, that's when we noticed the other 5 had failed. So this kind of points to what I was saying earlier, that repeated IR imaging can give us a good indication of the long-term performance of these things. Okay, so let's step into the validation and modeling a little bit here. One of our goals is to understand how to model these panels when they go into your facility. So the first step for us really was to determine the overall R value. And the way we did that is a standard conductance method. When you have a nice plan laid out and you've got the drawings, you can easily calculate the area that panels are filling. You can calculate your total wall area, and so you can generate a graph here. On the x-axis, you've got the percentage of failure, and on the y-axis, you've got the overall R value. That's an area-weighted average. So as you can expect, the more failed panels you have, the lower your R value is. The difference between these 2 lines here, we actually included the difference. The red line is just the wall, and the blue line is the wall considering any fenestration. So any windows, doors, mechanical rooms that would, we subtract those off so that we're not accounting for those. And as you can see, so we've got about 4% failure rate. We're still at about an R14 overall increase to the R value of the wall. One other thing to note here, you may have noticed in our previous pictures and figures, we went with a set of 4 different dimensions of panels. You may ask, why not just go with one big panel or a series of longer panels? There's 2 reasons for that. The first reason is it's the mechanical and thermal stresses that these panels experience during the manufacturing really limits their size to 20 or 20 to 28 inches, depending on the manufacturer. So it's really a limit of the mechanical stresses. However, perhaps one of the benefits of that is if you get a damaged panel, as you can see here, you're only really damaging a small section of the wall. You can imagine if our entire panel spanned this whole area, we would have almost lost, a quarter of this wall area if just by installing this sign. So there is an added benefit that it's a little bit beneficial if you do damage any panels, but it's kind of restricted to that area. So here's what we learned. We learned take extreme care when you're handling these panels. There will have to be, as this technology progresses, there needs to be care taken in installing it. Our partners at Oak Ridge are actually working towards creating or manufacturing 4-foot by 8-foot MAI panels, and these panels will be sandwiched between OSB or drywall. And the idea is, that would very quickly reduce the amount of installation time. If you have these 4-foot by 8-foot boards that you just stand up and you attach to the wall, that really reduces the labor and manpower for putting these on. But it also improves the durability. So your accidental scratches, your accidental, if you walk on it or if you drop something on it, the layer of OSB or drywall, depending on what it is, would actually prevent some of the damage to the panels. And so overall, it makes the whole board more effective. And here's the other 2 items related to the IR imaging. We can use it pretty successfully to see what panels have failed, and we can also use it periodically to show the long-term durability. Okay, so we have several sensors and instruments installed in this facility. Our goal, as I mentioned earlier, is to demonstrate the energy reduction in energy consumption, and also to show that these panels do help in reducing the energy losses through the walls. So we have a solar sensor there. We need the solar data for the EnergyPlus models. This figure 11 here is a temperature relative humidity combo sensor. The heat flux sensors, we put them on some gypsum and then screwed them on the inside of the wall. And in figure 13, keep in mind we did this in both buildings. So in the baseline facility, we only needed one set of sensors, temperature on the outside, on the exterior, and the heat flux on the interior. On the facility with the retrofit, we needed two sets of sensors, one on either side of the MAI. And the reason for doing that is, again, it helps us calculate heat flux, and it helps us create some better models as well. One other thing I'll mention here, we didn't do anything with the ceiling and the floor in the retrofit facility. One other place these panels can be used, the VIPs or MAIs, they can be used as ceiling insulation. However, that was outside the scope of this effort. In order to do the modeling, again, there's some baseline other test data that we need. So we conducted floor door tests. We needed to know the infiltration values for each of the facilities. On the natural gas, we put a pulse kit, and on the electric meters, we put in some watt nodes to log 15-minute data. Here's the results of our floor door test, the infiltration. The baseline facility actually had a lower infiltration than the retrofit. We call it a test building here. You can see there is some difference there in the CFM per square foot. After the retrofit, we actually saw some improvement. And the reason for this is, again, as I mentioned earlier, the MAI panels and the zip tape actually are both they're both barriers to air. And so if our entire facility had been covered with these panels, we would have expected a much better infiltration value. However, keep in mind, we used polyiso in between the panels, and that's porous. And so we expected some decrease in infiltration, and that's what we saw here. Again, this is maybe another side benefit or added benefit to MAI, but it's not really a primary benefit that we were looking at. Our initial data, I plotted a week here just to show or highlight a few things that we found were pretty interesting. So in this chart here, the blue is outdoor air temperature, corresponding to the right axis here. On the bottom axis, we've got days of the week. I've plotted about a week here, 4 days. And on the left side, we've got the energy. So this is just the natural gas. The red line is the baseline facility, the natural gas consumption in the baseline facility, and the green is the natural gas consumption in the retrofit facility. One interesting thing to note here, right after we installed the panels, we installed them on the week prior. On Tuesday, if you look at it here, when the building starts up in the morning, the peak natural gas usage is actually lower. It is lower in the retrofit facility than the baseline facility. So that gives us an indication that there is already some impact for these panels. And keep in mind, both these facilities are used pretty similarly. So some of that will be due to the occupancy differences, but it is pretty significant here. Another thing to notice, you can see that the retrofit facility, there's a lot more cycling here in our natural gas, and that is an effect you would expect as you increase the R value and the envelope becomes better. Your heating and cooling does not needs to cycle a lot more because you're suddenly reaching your set points much quicker. And so one of the things we'll look at as part of our ongoing efforts is, this is a detrimental effect in some sense because increased cycling increases the wear on your components. So it's a trade-off between reduced energy usage and increased wear and tear on your components. So that's one thing we will be looking at. So that was just for 1 week. If I plot here the overall consumption over the last many months that we've had the data, you can roughly see there is the overall decrease in energy consumption. And so quantifying that about 11 or 12% overall just from the raw meter reading. This does not account any occupancy effects. It still does need to be built in. But these facilities are pretty lightly loaded. There aren't people in that building all day, and so we don't expect that to have too much of a change. Interestingly enough, this is something that we were not expecting, is that the electric consumption stayed roughly about the same. In fact, there was a small increase. We've gone back to the site. We found that there is some additional server loads that are not within the building. They're actually in the mechanical room. But that does have an impact on our overall electric use. So we need to factor that out and account for that. Here's some data from the heat flux sensors. This is really where we expected to see a drastic change, and we do see that. The blue lines here are the baseline facility, and the red are the retrofit facilities. And we've got time here on the x-axis, and on the y-axis we've got the heat flux. And so you can clearly see there's a significant decrease in heat flux through the walls. If you account for that now, again, depending on the facility and where it's facing and the dimension, this will all change. So on this wall, the south-facing wall, we see about 62% decrease overall. I'm sorry. Okay, this is not the south wall. I believe this is the east wall. The south wall, you see something similar. Again, the red is the retrofit facility, and the blue is the baseline. And again, we see a pretty significant decrease. When you average it all out across all your different walls, it turns out to be about a 20% decrease. So one of the things that went against us or against this particular demonstration is it was difficult for us to find a facility that was not insulated. And so when you go in to a facility that already has insulation, it's really a rate of diminishing returns. So, keep in mind this facility already had R13, and when we put on this insulation, we saw an additional 20% reduction. This technology is probably best used in new facilities and new construction. That's where you're really going to get the best economic impact. And it's much easier to include this in your early design and planning phases, so you can actually reduce the overall cost of the installation as well. But again, we didn't have that the luxury of doing that for this project, and so we kind of had to go the retrofit route. But again, it is effective. It does still reduce your overall heat flux by 20%. And those values do depend on the winter and the summer, at least for this site. So now we have all our data that we need. We have all the sensors. We have all the data we need. How do we create the energy model? Well, the way we did that is, again, number one, we start with the details of the building. We have interior measurements, we know the dimensions, we know the type of insulation, lighting, occupancy. We've collected all the details we need for the facility. And so really it's now an exercise in developing and improving your building model. So our validation method here is to create our models and then see how our heat flux behaves. If we can get our heat flux to match the actual conditions, we have some comfort in knowing that we have a pretty good model, and then we can back out the electric consumption and the natural gas from that. So really, put it simply, we look at the heat flux. We want to try and get close on the heat flux, and one step above that, after we're sure that our heat flux is correct, we can step back and have a look at our energy consumption. And the reason we're doing this modeling is two reasons. One is there are lessons learned here that I think are pretty important moving forward as this technology matures and progresses. But number two, in order to get an accurate understanding of our savings, we have to remove the occupancy effects. That's something that you necessarily cannot control for in each facility, so we're trying to get to understanding the reduced energy consumption just for the technology itself. So for those of you who are familiar with EnergyPlus, you do need to set some boundary conditions. The way we did that here with our weather, we had temperature data from the Wheeler-Sac Army Airfield, and we also had on-site from the weather station. Unfortunately, our weather station on-site had some data issues until just a few months ago. So we're collecting good data now. We did have to use some data from the airfield, which is within 5 miles. It was pretty close, but not exact. In your EnergyPlus model, the other aspects that we put in was the construction, the location, and the R value of our MAI. If you recall, early in the presentation, I showed a graph of R value as a function of temperature. That's one thing that we have not considered yet in our models, and that's our next step. But as an initial baseline model, just to make sure we had something sensible, we went ahead and just put an average R value in there. And on the interior side, we also have data on the occupancy schedules and air temperatures. One issue we did run into is one of our interior temperature sensors had a fault and was not recording data for many months. We did fix that, but we had to use an alternate approach there for the modeling during that time. So I'll talk about that here in the next slide. But before I get to that, this is what our facility looks like when it's modeled. Again, as I showed you earlier, it's a pretty simple facility. We know the dimensions of all the zones. We know where the windows are. We know any overhangs. So again, it was easy for us to at least come up with an exterior model. This facility is right here. We've got a shading aspect because depending on where the sun is on the sky, this building does cause a shading effect on the other building, and that's what this part of the model is there for. Our interior boundary conditions was the interior air temperature. So ideally what we'd like to do is feed EnergyPlus the interior air temperature and have it calculate the heat fluxes. However, as I mentioned earlier, we did not have that luxury in one of our facilities because the interior sensor had failed. We do have some thermostat data that we'll feed back into it, but we're still working on that. So what we have to do in the meantime is assume very high convection coefficients. So if you recall, we have sensors on the interior of our walls, very close to the walls, and so we had to assume, in the absence of other data, we had to assume that our wall temperature was close to our room temperature. We knew it would be wrong. We knew it would not be accurate, but we had to try it and see what kind of results we get. So here's the results we get from that. And it's a little bit interesting, actually. In each of these graphs here, this is the baseline building on the left, and on the right we've got the retrofit facility. The red line is the measured exterior wall temperature given all our initial boundary conditions, and the blue is the simulated. So you can see, and what you'd expect is the simulated tracks the trends of the measured pretty well for both facilities. However, during the daytime, the peak times for when you have the most solar insulation on the building, it actually is off by, you can say, a pretty significant amount. In some cases, almost 10 degrees or so. And so that's something that we found was interesting. Part of the reason for that was, again, the issue I mentioned with the high convection coefficient actually throws the model off. And so when you have a lot of factors such as solar and other items, it ends up not working out so well. During the nighttime, however, it's pretty close because you're getting rid of some effects at that time. So we did also have some issues with our solar measurements, which kind of compounded the effect as well. And so bottom line here is if you do validate, measure and validate this technology, our heat fluxes are matching up somewhat with what we see. It is an appropriate validation method. We just we're missing some of the data here. And so that's what this last bullet points towards, is that the heat fluxes were erroneous, and it was because of the assumption we had to make. So in our modeling and validation, what we found is it's very important to get the air temperatures on the interior. Without that, it makes it difficult to make a model. One way to fix that is, if you don't have interior sensors, but you do have wall sensors, you can actually place the wall sensors about 6 inches away from the wall, and what that does is it collects the room temperature pretty well. A couple items we do need to follow up on and work towards in order to improve our model is to account for the R value as a function of temperature, but also to include some of the internal loads when we get to that point for light and occupancy. So what we have learned from our data, and hopefully this is beneficial for future aspects when we try to bring this technology to its potential and really start rolling out more demonstrations, is we do see a decent amount of reduction, about 11-12% in natural gas consumption. As I mentioned earlier, electric consumption actually went up a little bit, but that's because of some other interior electric loads that we did not account for, and 20% overall reduction in wall-related energy losses. We do have some work to do in our EnergyPlus models. As I mentioned, we had some issues with our sensors. We're working on fixing those. And as we learn more from our models, we expect to be able to simplify them. So, for example, if you wanted to use EQuest or something else that wasn't as detailed as EnergyPlus, we expect there's a lot of simplifications you can make to your models to account for much of these variations. And the last thing we'd like to do, again, the goal here, finding out exactly what the benefit of the technology is on energy consumption. Once our models are accurate, we'll account and remove all the occupancy loads, and so we can get a true measure for how much we're saving. Again, our initial data shows that we do have some pretty significant savings. We just need to get a little more accurate on that. And once we do that, we can get a fair idea of the economic impact or economics of these systems. All right. Well, that's all I have. Any questions for me?
The first one we have is, what is the typical cost per square foot over standard insulation? Like how much more is it than the polyiso or something like that?
Okay, let me put these numbers here again real quick. So if you want to say per square foot, it's roughly, okay, I see, I have this per square foot per R value here. So I think, roughly speaking, if you're looking for the same amount of polyiso, polyiso is probably half the cost of where we stand at this point to achieve the same R value.
Oh, okay. Someone else commented they noticed that there was more energy savings on one wall than on another. In the interest of saving money, would you only put the insulation on 3 walls, leaving out the one that really did not save so much energy, or does this create a heat sink?
That's an excellent question. I don't know the answer to that. I think this is the reason. Let me pull up that slide here real quick. I think the reason we saw this kind of variation is really just a function of the building layout. The ducts for the HVAC system, the supply ducts are not exactly in the center of the building. They're located in different areas. So that's part of the reason we saw some of these effects. And this facility, the north wall, actually also had a poured concrete section in there. It used to be used as an arms vault, and so that added some additional insulated properties that we wouldn't normally expect. So I don't know the answer to that question. I wouldn't think that it would make a huge difference. In most cases, I would probably recommend insulating all sides of the building. We all know that we could easily model that, but it just really becomes a question of how much can you trust your models, and how do you justify, or can you justify only doing certain sections of the building? And not to mention, if you do that, you start really messing with the heating and cooling across the building, and so occupancy comfort, then, if for example, I only insulated the east or the north side, then those occupants would either be really hot or really cold compared to the others. So I would not advocate that, but I don't know the answer to that at this point.
Okay. You mentioned the tape that was applied to seal the panels together. Could you describe what kind of tape that was?
Yeah, so it's called zip tape. That's actually the brand that's used there. It's you can get it at Lowe's, Home Depot, really any of the big chains, and it's a very good tape. It basically creates a impermeable barrier, and so that's what it's used for. It's using existing home construction activities.
Okay.
So the point of that again was to stop little air convective currents between the panels.
Air infiltration and things like that.
Correct.
Now, do you have any data on the noise reduction attributes?
We do not. We did anecdotally ask occupants on that on a survey. They say they do notice some benefit in noise reduction, but we have not quantified that.
Mm-hmm. Okay. I mean, foam in general is pretty good, so if it's, I think that it'd at least be pretty good with respect to that. Certainly wouldn't make it any worse, I can imagine. But
right.
How many manufacturers of MAI panels are there on in the U.S. market now?
So MAI, as far as I'm aware, there's only one. VIP, there's several, and since we have a few minutes, I'll talk real quick about how MAI is different. So what they do is, instead of pulling a vacuum, and then this is all technology, it's all patented, so I'm not giving away any trade secrets here, but VIP, typically you have a core that you pull a vacuum over and then you wrap. MAI, the manufacturer, actually introduces steam into your panel, and when you do that and then you cool it down, you're essentially achieving the same effect of a very low partial pressure. And so, it's much cheaper to do it that way. Instead of pulling a vacuum, you just insert some steam and then let it cool down, and that actually has the same effect, or at least as good of an effect. So that's how they're reducing, to some extent, their manufacturing steps and also the cost.
Okay, right, because very hot, the steam is very hot, like a hot air balloon inflates, and so then when it cools down, it contracts, and then essentially pulls a vacuum if you seal it into a tight space.
Correct.
Okay, so there's not necessarily any, this is modified atmosphere, so it's not really any different in terms of the air. It's not any special gases or anything like that.
No, the only expectations I would have is that this may behave a little differently under extremely warm conditions. Because it is steam starting out, you probably have some more molecules than you would under traditional VIPs.
Mm-hmm.
So it may not behave as well, but at least from the data we collected, that's not a significant enough difference.
The manufacturer that's out there, and maybe also the VIP manufacturers, are there enough on the U.S. market that meet the Buy American Act? Or does the MAI panels meet the Buy American Act?
They would meet the Buy American Act. From my understanding, many of the manufacturers, not all of them, many of them are smaller businesses, and so they're still trying to get to a commercial scale. And so again, depending on what your objectives are for the construction or retrofit of a facility, the cost may be one of the barriers. There are larger companies working towards it, but again, the cost is kind of the important consideration here. So there are many manufacturers, I'd say at least 10 or 15, if not more, that make the VIPs, and it's all made and manufactured here in the U.S. So I believe it would meet the Buy American requirements.
Okay. Is there a process for the Uniform Facilities Guide Specifications, the UFGSs? Will there be a spec section on MAIs, or will the VIP spec sections under development include them, or how will that work?
Yes. We are going to be looking at that, and certainly if anyone on the call here would like to reach out to me and maybe we can talk through some of that. We are still trying to determine the impact of these, so once we have some good data and we're comfortable with the data, that's our next step, is to try and look at the UFCs and UFGSs for specifications and criteria. So we're not there yet, but I would certainly entertain some conversations. I would like to talk with some folks that eventually would be involved in the design and implementation of this, and so that will help us come up with some requirements. So please feel free to shoot me an email, and I'll respond back as soon as I can.
Right, especially these technologies that can be very useful when you're in existing spaces. We're seeing more SRM work being our meat and potatoes of the work coming forward now that bracket's finished and all that. So things where you have a limited, like if you have clear story windows over a roof deck or something like that, you might not have enough thickness available to be able to put a lot of insulation in. So VIPs and these MAIs can really help solve a problem even though they are more expensive.
That's an excellent point. I forgot to mention that, yes. When you have constrained spaces or distances, and you can't put in any traditional fiberglass or anything like that, this would certainly help get towards that. So, good point.
Okay. Now, for installation that with using these panels, since they are relatively new, have you heard of them being able to count for an innovation point with the lead scoring?
No, unfortunately, I've not I've not heard of it, so I'm not sure of the answer to that.
Okay, I'd pursue it as an idea to get 2 banks for the buck for the installation and energy savings, as well as get a point for that, as well as a point for the innovation. I'd at least argue it and see what they do.
Yeah.
All right. Well, we are at the top of the hour, and I want to thank you again, and thank everybody else who attended. Excuse me, got a little congestion here. So Tapan, thank you as usual for joining us, and some editing on it, and hopefully get it up on our YouTube channel and on the Mercy site next week. And Kelli will be putting the quiz up there for those of you who are interested in CEUs. So I think I believe our next one is October 4th, and that's on the Internet of Things, and so that should be interesting as well. Thank you again.
All right. Thanks, everyone. Thanks, Eric. Talk to you soon.
Right.